Students, so we are going to continue. Good afternoon, students. We are going to continue the second part of Unit 5, that is single phase induction motor and special electrical machines. So far we have seen the construction, working, and different types of single phase induction motor along with its phasor diagram and characteristics. We have also compared the torque speed characteristics of different single phase induction motors. So based on the characteristics of single phase induction motors, it can be chosen for different applications. So as I said earlier, specifically single phase induction motors founds its major roles in maximum residential applications and few of the industrial applications too. So here in the slide you can see different machines like mixie, wet grinder, the pump motor, ceiling fans, vacuum cleaners, drilling machines. So like this, many of the domestic and few industrial applications, they make use of single phase induction motors. So based on this specific application, so we can also replace the single phase induction motors with specially designed electrical machines. Say for example, the ceiling fans nowadays, the single phase induction motors are replaced by BLDC motors. In vacuum cleaners, they are replaced by hysteresis motors. Like that, specific application. So it needs some specific characteristics. Am I right? So to meet up these characteristics, slight modifications are made in DC as well as AC machines to make it suitable, very much suitable or affordable for the particular specific application. So to meet this requirement, we are going to see about different special electrical machines and where we can use those machines. What are the characteristics of the machine? What is the application like that? We are going to see in this session. Okay. So special electrical machines. So in this session, we're going to see about these 6 different types of special electrical machines: stepper motor, servo motor, hysteresis motor, AC series motor, repulsion motor, and linear induction motor. Stepper motor, servo motor, hysteresis motor, AC series motor, repulsion motor, and linear induction motor. And along with this, we're going to also see, so what is that magnetic levitation principle? Because so it is one of the important applications nowadays which the researchers are focusing on. It makes use of some special machines on this. We will be seeing this at the end of the session. Okay. So first, let us see stepper motor. So what is this stepper motor? What is the basic difference between a normal AC or DC machine and this stepper motor? A stepper motor is normally a digital actuator, or it is and DC, brushless DC motor. A stepper motor is a brushless DC motor because so in stepper motor rotor there is no windings. Since there is no winding and there is no need of any excitation given to the stepper motor rotor, there is no need of any brushes because brushes are meant for giving in or taking out that supply or voltage, the electrical power from a machine or to the machine, to give electrical power to the machine, rotor, or to take the electrical power outside, we will be making use of brushes. Since in the rotor there is no winding and we are not going to give any supply to that, brushes are not required for this machine. So it is a brushless type. And the input is C, so it is a brushless DC motor. Okay. So unlike other conventional AC and DC machines, this stepper motor, it will not rotate continuously. Instead, it will move step by step. So for each input command pulse, the stepper motor will move for one step. For one command pulse, stepper motor will move for one step. So it is designed, it is controlled by the required controllers. So the pulses are controlled by the controllers. Based on that, the stepper motor will move from one position to another position So the angle swept by the stepper motor rotor is known as step angle. Okay. So this is the basic construction of stepper motor. So you can see as similar to as like any other machine, the stepper motor is also having stator and rotor. In the stator, we'll be having the concentrated windings, concentrated phase windings to which I'm going to give excitation. Say for example, if it may be a monofiliar winding or it may be a bifiliar winding. That is the winding sets. Say for example, let us consider the phase A. So this phase A will have two coils in it. One coil A, another coil A dash. If A and A dash are current in phase, then this is known as monofiliar winding. For bifiliar winding, this A and A dash coils are magnetically coupled, magnetically or inductively coupled, and there is no electrical connection between A and A dash. Like that, if the coils are made, they are known as bifiliar coils. So it may be monofiliar or bifiliar, but it will present this. It will be placed in a concentrated manner in the stator poles. Okay, in the rotor of stepper motor, generally there are three basic classifications of stepper motor which are divided based on the material as well as the structure of rotor. Okay, so there are three basic types. One is variable reluctance stepper motor. Second one is permanent magnet stepper motor. The third one is hybrid motor. So this variable reluctance stepper motor is nothing but if the rotor is salient pole shaped, the rotor is salient pole, that is poles are projected from the rotor core. If from the rotor core, if the poles are projected outwards, we used to call that as salient pole. So salient pole structured and ferromagnetic material is placed in the variable reluctance stepper motor. In permanent magnet stepper motor, the rotor is somewhat cylindrical in shape, cylindrical rotor, and it consists of permanent magnet. It is made of permanent magnet. So salient pole, ferromagnetic material, it is variable stepper motor. Smooth cylindrical permanent magnet, it is permanent magnet stepper motor. And if we combine these two things, that is, if you are taking the shape from variable reluctance and taking the material from permanent magnet stepper motor, and if we combine these two things, you'll be getting hybrid stepper motor. That is salient pole shaped permanent magnet is present in hybrid stepper motor. These are the three basic classifications of stepper motor. Now let us see how this machine works, how these machines are excited. Say for example, if I am considering two phases or okay, two phases A and B. A and B. Let us consider two-phase stepper motor. So here the phase represents the windings. The supply they are going to give is still DC. The phase represents winding, set of windings. Okay, so consider two-phase winding A and B. Let us consider two phases A and B. It is not similar to a red, yellow, blue, or it's not like three-phase, two-phase connection. It is simply two set of windings. Okay, I'm naming it the winding as phase winding A and phase winding B. If at a single moment, if I'm going to excite only one phase at a time, that is, you see here, the input pulses are given. So initially, the waveform represents A phase. So once A phase is turned off, the B phase is turned on. Once the B phase is turned off, again the A phase turned on. Once the A phase turned off, again the B phase turned on. So at least at a time, only one phase is turned on. So this type of single phase excitation or single coil excitation, so it results in holding and running torque reduced by 39%, increased efficiency but poor step accuracy. These are the various features of single phase on mode. So in dual phase or two phase on mode, at a single time, two phases will be turned on. So if you see here, at this moment, phase A as well as phase B is turned on. So here again phase B and phase A dash is turned on. Again phase A dash, then phase B dash is turned on. Like that, at a time, two phases are turned on. So if two phases are turned on, two set of coils are turned on, then it is known as dual phase mode. Then the third type of excitation is alternate one phase and two phase on mode. Here it is a combination of first two types. That is, initially A phase is turned on, then we'll be going for AB. Then B phase is turned on, then you'll be going for BC or B A dash. Then A dash is turned on, then A dash B dash. Then B dash is turned on, B dash A, like that. One phase, then two phase. Again one phase, then two phase. Like that we'll be giving excitation. So that is the third type. One phase, alternate one phase and two phase on mode. So the second type, dual phase on mode, it is having good starting torque and good step accuracy. If you go for third one, so the combination of these things, it results in poor step accuracy, but good resonant characteristics, higher pulse rate, it requires higher pulse rate, and half stepping is possible. First two type of excitation, single phase and dual phase excitation, it is known as full step operation. Nothing but the angle swept by the stepper motor rotor is known as step angle. If the step angle is equal to one full step, it is known as full step operation. Say for example, for a machine, if the maximum step angle parameter is 30 degrees, which depends on number of stator tooth and number of rotor tooth and the number of phases. If the maximum step angle permitted is 30 degree for a machine, and the first two excitation methods, it will be 30 degree, whereas the third method, alternate one and two phase on mode, it is half step operation. That is, the rotor will move for 15 degree instead of 30 degree, half step. Okay, so this is alternate one phase and two phase on mode. There are few other methods are also. Say for example, the next advancement is microstepping. Microstepping, one phase is turned on. Say for example, A phase is turned on, and B phase will be divided into different steps. Say for example, instead of turning on completely from 0 to 1, the B phase is turned on from 0 to 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.8, 0.9, 1. So that 0 to 1 is divided into 10 equal steps. But what will happen here? So if B phase is turned on, if the rotor is going to rotate for move for 30 degree, if it is divided into 10 equal steps, the 30 degree, it will be divided into 10 equal steps. The meaning is that the rotor will move for 3 degree for each step. What will happen? So in single phase and two phase on mode, the angle will be 30 degree. In alternate one phase and two phase on mode, the angle will be half step operation. That is 15 degree. In micro stepping, by reducing that by increasing the number of steps, we can even further divide the step angle, and we can the maximum step angle that we can get for a machine using micro stepping is 20,000 steps. Just imagine a machine with 20,000 steps per rotation. It takes 20,000 steps to complete one rotation. That is, the meaning is that for each given pulse, the rotor will move for 0.018 degree. So if a machine moves for 0.018 degree, to complete one rotation, that is 360 degree, the machine will take 20,000 steps. So this procedure is known as micro stepping. Okay. So next thing, so one by one, let us see different types of stepper motors. First one is variable reluctance stepper motor. So as I said earlier, it is plain iron rotor or ferromagnetic material rotor. So there will be a minimum reluctance between in the air gap. It was on the principle of reluctance principle. The rotor point attracts towards the stator pole. So whatever the phase is excited, the rotor pole is made to move. In order to maintain the minimum reluctance, the rotor will start to create torque, and it will get aligned in the excited phase, aligned straight to the excited phase. Say for example, if this phase 2 is energized, so this aligned pole, it will move for an angle of 60 degree, and it will reach this phase 2, get aligned with phase 2. Like that, the machine will rotate. So whatever the phase is energized, the machine will be trying to align with that particular phase, because it works in the principle of minimum reluctance principle. That is, what is the minimum reluctance principle? Whenever a ferromagnetic material, if it is placed in the magnetic field, what will happen? Whenever a ferromagnetic material is placed in the magnetic field, it will tend to align in the minimum reluctance path. That is, in straight to the phase which is excited. So whenever a ferromagnetic material is placed in the magnetic field, it will tend to align in the minimum reluctance position. That is the minimum reluctance principle. Clear? So the next one. So for this machine, one phase on mode, that is full step operation. So if you see here, as said earlier, at a time only one phase excited. Say for example, initially A phase is excited, the angle it is initially it is near A, it is straight to the A phase. So angle shot is 0 degree. Then B phase is excited, that is B is given plus, meaning is that B phase is excited. So here is the B phase. The rotor 1, the pole 1 and 3 will sort for an angle of some angle. What is the nearest pole to this B phase? It is pole 4, right? So 2 and 4. So 2 and 4 is the nearest pole to this B phase. So this pole sets 2 and 4 will move in clockwise direction to get aligned with B phase, So the angle shot is, so this angle is 60 degree. So half of this angle. What is the angle shot? It is 30 degree. 30 degree to shot. Then this is the second position when B phase is energized. Then if C phase is energized, so this is C phase. So what is the phase? What is the pole which is near to C phase? It is 1 and 3. So when C phase is energized, the 1 and 3 will get aligned with C phase. So again, one will move for again 30 degree. So in order to get aligned with C phase. So 30. So step angle will be 30 here. The rotor will move like this. When it comes to two phase on mode, the same procedure, but what will happen is at a time we will be exciting two phases. Say for example, AB will be exciting AB, then BC, then CA. So A plus B plus angle 15 degree. Then BC, then B plus C plus again 15 plus 30, it is 45. Then again CA. CA now, what is the meaning of CA? C plus, then A plus. C plus and A plus. Again 45 plus 30 degree, it is 75 degree. Like that, it is still is a full step operation because the angle difference between the consequent step is 30 degree. The next method, alternate one phase and two phase on mode. What is the meaning of alternate one phase and two phase on mode? So initially one phase is turned on. Say for example A, then AB, then B, then BC, C, CA, like that. Alternatively, one phase and two phase will be turned on. Say for example, it is a combination of first two types. So 0 degree, 15 degree, 30, 45, 60, 75. So angle difference between the consequent step is 15 degree, which means for full step it is 30 degree, for half step it is 15 degree. So the machine, now for alternate one phase and two phase on mode, the machine will work under half step operation, half step mode. Clear? Half step mode. Then the last one, which I said earlier, micro stepping. So what is this micro stepping? In micro stepping, if you see, instead of giving a complete pulse, it is divided into different steps. So if you see micro stepping, you can see here, it is divided into different number of steps. So based on these different steps, for each step, the rotor will move for a discrete angle. You can see how the rotor will move for discrete angles. So this is how it happens. So rotor will move for some discrete angle. Clear? So say for example, if for a complete step, the rotor moves for 30 degree. If each pulse is divided into 10 equal steps, then 30 degrees is divided into 10 equal steps. That is, for each step pulse, the rotor will sort for 3 degree. So like that, it will cover 30 degree in 10 steps. 10 steps. Okay, like that, the machine will rotate. Clear? So the second type of stepper motor, permanent magnet stepper motor. As I said earlier, what is the permanent stepper motor? It is of cylindrical in shape with permanent magnetic material is used. So here, along with the manipulations, what will happen? The stator we are going to excite. In the rotor, there is a permanent magnet. What will happen? Magnetic lines of force. So magnetic force of attraction and magnetic force of repulsion which takes place between the stator poles and rotor poles. It makes the machine to rotate. So if you are continuously changing the stator excitation, the rotor will start following the stator excited phase. Like that, the machine will start to move. That is what happening in permanent magnet stepper motor. Here also we can see the one phase on mode, two phase on mode, like that. So different methods here also we can observe. Say for example here in one phase on mode, that is full step operation. Initially it is excited to A phase, that is A plus. then it is excited to B phase. It is B plus. So rotor rotates for an angle of 90 degree. Then the third condition, it is A minus. So A minus. So again the rotor will rotate for again some 90 degree. It is 180 degree. Then again B minus. So 270 degree. Again finally A plus. So again finally A plus. There it is 0 degree. So 0, 90, 270. 180, 270, then again 0. So like that the cycle repeats. This is one phase on mode or full step operation. Second one is two phase on mode. In two phase on mode, what will happen? We will be exciting two phases at a time. That is A plus B plus, B plus A minus, A minus B minus, B minus A plus B plus. Like this the cycle repeats. So this two phase on mode is also, it comes under full step mode. So initially the angle is 45 degree, then plus 90 degree, full step 90 degree, angle becomes 135. 135 plus again next of 90 degree is 225. 225 plus again 90 degree, 315. 315 plus again 90 degree, it is 360 plus 45. So like then it is 405. It can be written as 360 plus 45. Like that we can divide. So this is what happening in two phase on mode of Coulomb magnet stepper motor. So alternate one phase and two phase on mode. So here, as said earlier, alternatively one phase and two phase is turned on. It is the combination of first two methods. That is full step one phase on mode and alternate two phase on mode. So it combines alternate one phase and two phase on mode. So it is an half step mode in which the angle step will be, if the full step is 90 degree, then the half step will be 45 degree. So initially it is 0, then it comes to 45, then 90, then 135, then 180, 225. 270, then 0, like that the machine will start to rotate. That is what happening here in alternate one phase and two phase on mode. That is half step operation of Coulomb magnet stepper motor. So third type of stepper motor is hybrid stepper motor. What is this hybrid stepper motor? So this hybrid stepper motor, it is the combination of variable reluctance and Coulomb magnet stepper motor. So here these are the different types. So if you see this image, you can clearly understand what is this stepper motor. So here you can see the permanent magnets are placed here. The shape is salient pole. Permanent magnet, salient pole. So this type, this side of permanent magnet is north pole and this is south pole. A cap is put over that. So the cap becomes, again the cap is converted into north pole and this cap is converted to south pole. So like that the machine will be there. So if you see, the poles are, the magnets are aligned such that the alternate pole arrangements are between the rotor caps. Say for example, this is my south pole and this is my north pole. So in between there is a gap. You can see it is not straightly, it is not aligned. This is my south and this is my north. South, north, south, then north, south, then north, south. So it is not aligned directly, straightly. So it results in it, but a torque, and it will help us to avoid magnetic locking. Okay, so this is what happening in hybrid stepper motor. So hybrid stepper motor. So if you see the application of hybrid stepper motors, so the basic advantage of stepper motor is that stepper motor can work under open loop condition itself. So it is very precise and the control is very easy even under open loop condition itself. Variable step machines like variable stepper motor, so they does not have any rotor winding, so there is no rotor copper loss. So since there is no rotor winding, the rotor weight is low, so the machine is having better inertia. That is the machine is having low inertia, which makes the machine to move quicker. So the control is easy, the open loop control is possible. So like that, it is having plenty of advantage with it. So this is the application of stepper motor. So stepper motor found application widely in many industry, starting from domestic application to satellite communications. So here we have shown few applications like robotic arms. Stepper motors found wide application in robotics, in drilling bits, in drilling equipments, in clocks or many timing devices, in CNC printers, in CNC machines, in faxes and printers. So in all these applications, stepper motor found its ideal suitable application like there. So this is all about stepper motor. Next machine we are going to see about AC series motor. AC series motor. So what is this AC series motor? So an AC motor with commutator and brushes assembly is referred to as commutated motor or AC series motor. So literally, if you see, it is similar to that of an DC series motor. What is the DC series motor? There will be two windings, armature and field. If the armature and field, if both are connected in series, and if DC supply is given, then the machine is known as DC series motor. Then what would be an AC series motor? An AC series motor, similarly, similar to a DC series motor, it will be having an armature winding and field winding which are connected in series to each other. So what happened if AC supply is given to DC series motor? What would happen if a normal DC series motor is given an AC supply? So there are three basic problems will occur. Okay, first one is due to the fact that the current will change continuously because of AC supply, the power factor of the machine it will be very much poor. So first point, power factor is poor. Second point, so it results in more induced EMF and more eddy current loss will takes place. More eddy current loss. Third one, sparking of brushes. Sparking occurs at brushes. So there are three basic problems which we are facing when an AC supply is fed to an DC series motor. Low power factor, eddy current loss, and sparking of occurs at brushes. How to overcome this loss? So the modifications required are the power factor can be improved by what will happen? So the power factor, if the power factor need to be improved, then we need to reduce the number of turns in the armature winding. Reduce the number of turns in the armature winding, so that the reactance will reduce. The reactance will reduce, then it will result in better power factor. But this reduction in reactance, which will result in increase in speed. Increase in speed again will result in decreased torque, and again to improve torque, we need to go for increase in turns. So there is an undesirable controversy between these two things. So consider all these things. What we need to do is the proposed final modification is that let us go for an compensating winding. So which will compensate the loss in turns in armature winding. So we'll be adding one more compensating winding which is connected in series to armature winding. Whatever current flows through the armature winding will flow through the compensating winding also. So it results in better power factor. Then the second problem what we have seen is eddy current loss. So how to reduce eddy current loss? If we are laminating the stator core, will be considered the eddy current loss can be considerably reduced. The third point is sparking of brushes. So sparking of brushes can be avoided by using interpoles. Okay. So here, if you see the compensator winding, how it can be connected? There are two types of connections of compensating winding. One is conductively compensated. That is, it is connected in series with the armature winding. Electrically series the armature winding. If it is inductively coupled, then it is known as inductively compensated machine. So there are two ways by which the compensating winding can be connected, and that sparking can be avoided by using commutating poles, which are also known as interpole. Interpoles are present. They are small auxiliary poles which are present between a set of main poles. So it will try to compensate the problem which is occur due to sparking. Okay. So even after the addition of compensating winding or compoles or interpoles, this more EMF is induced in the current, more current flows through the compensating winding, and it results in again there is sparking of chances there. Then how we can avoid this? That is by connecting one more resistance parallel to the compoles or compensated or interpoles, and by varying the resistance, the current flows through the current responsible for sparking can be adjusted, and the sparking can be reduced. This is how AC series motor operates. So it operates as like a normal DC series motor. The basic difference is that the input is AC. So there are three basic problems which will occur if AC supply is given to a DC series motor. The first one is poor power factor, second one is eddy current loss, third one is sparking. Poor power factor can be reduced by reducing number of turns, and it can be compensated by n compensating winding. And second one, eddy current loss is reduced by proper lamination of stator core. And the third one, sparking can be reduced by connecting an interpole. Again, interpole connected in series parallel with the resistance, that is a variable resistance. So if the variable resistance value is changed, then the current flows through the interpoles will also change, which will result in less sparking in rotor. So this is what happening in AC series motor. This is the characteristics, torque speed characteristics of AC series motor. If you see, the AC series motor is having a torque speed characteristics more or less similar to a AC series motor. The difference is that there is a slight reduction in the value of speed and the value of torque. So this is what is happening here. Or the speed torque relationship. So that is slightly lesser in AC series motor compared to DC series motor. Applications of AC series motor: hair dryer, portable drilling bits, hair dryer, fans. So these are the applications of AC series motor. AC series motor can be also called as universal motor because it will operate both at AC as well as DC. So it is also known as universal motor. Clear? The next type of machine is repulsion motor. So what is this repulsion motor? Why it is known as repulsion motor? Why the word repulsion is here? So it is an interesting topic. So it is an 75 horsepower repulsion motor, so which is referred in Wikipedia. So you can see the image in the Wikipedia itself. So it is a very old conventional machine, repulsion motor, but the working principle is very innovative, and it's a very good machine. So if you see, this is the basic construction of repulsion motor. Here, there are two sets of windings. One is the stator winding and one is rotor winding. Here in the rotor, you can clearly see the brush is short circuited. The brush is short circuited. So in the rotor, the brush is short circuited. So this is the armature, and in the rotor, the brush is short circuited. So what will happen if the brush is short circuited? So before going into this, we need to know about two axes. One is direct axis, another one is quadrature axis. That is, the axis which is along the brush axis is known as direct axis. The axis which is along the brush axis is known as direct axis. The axis which is at 90 degree to brush axis, at this position, 90 degree to brush axis, or quadrature to the brush axis is known as quadrature axis. So there are two axes, and with this axis, direct axis and quadrature axis, and the position of armature MMF or the stator flux MMF, so it will decide the operation. So to explain the operation, consider four different cases. One is the brush axis is parallel to the stator MMF or magnetic field. Second one is the brush axis is perpendicular to stator magnetic field. Fourth one is the brush is shifted clockwise direction. The third one, brush is shifted clockwise direction. And the fourth one, brush is shifted in anti-clockwise direction. So if the brush is parallel to the armature EMF or magnetic field, then there is no proper EMF is induced, and it results in the distribution of equal distribution of flux in both the sides, which will get cancel out each other, and the net value will be 0. And if we take at a perpendicular direction, again it will result in 0 net induced EMF, net value in the rotor. If it is displaced, say for example 45 degree to the stator MMF, axis of stator MMF, in the clockwise direction, the machine will start moving in clockwise direction. If it is placed 45 degree in the anti-clockwise direction, then the machine will start moving in anti-clockwise direction, like that. machine will start to move. So it should, the repulsion motor, it should not stand along its direct axis to the magnetic field, stator magnetic field, or should not be straight with the quadrature axis of quadrature axis. So the magnetic field should not be aligned with direct axis, and the magnetic field should not be aligned with quadrature axis also. So the brush axis should be repelled from the stator MMF axis, the axis of stator MMF, to a maximum angle of 45 degrees. So that is why the machine is named as repulsion motor. That is why the machine is named as repulsion motor. So the repulsion motor, it is having good starting torque. It has good speed regulation. For certain heavy loads, the torque can be developed. Starting current is also less for repulsion motor. The basic disadvantage is that, as I said earlier, the power factor is low, eddy current losses more, and these things, sparking of brushes are there. So these things can be avoided by making suitable modifications. The application is that, so they are used in film winding machines, and they are using compressors, textile machines, and various industrial applications. They are using repulsion motor. Okay. So in this session, we have seen 3 different special electrical machine. One is stepper motor, second one is AC series motor, third one is repulsion motor. Okay. So hope you understand the session. Thank you.